is probability. So 2.1, we're going to start with a couple definitions. So what is probability? Well, probability is just the likelihood of an event happening. Or maybe should we say occurring? Okay, and what is an outcome? So when we talk about outcome, we talk about a possible result of an experiment. Okay, so possible result of an experiment. Okay, so for example, if you are tossing a coin, you could get a tails or a heads. If you're rolling dice, or a die, you could get a 1, a 2, a 3, a 4, a 5, or a 6. Okay, those would be the possible outcomes for those events. Okay, and an event is a set of outcomes with the same result. Okay, set of outcomes. With the same result. Result. Okay, and all that is for example, tossing a coin. Toss a coin would be an event. Okay, or rolling a die. That would be an event. So the event would be tossing the coin, and then the outcome would be the actual, like, did it land on heads or tails. And a trial. A trial is just one round of the experiment. Okay, so one round of an experiment. So it would be tossing a coin once or rolling a die once. Okay, the actual toss a coin, and that would be once. So one trial. Okay, and what is a probability, or sorry, experimental probability? This is when you actually do something in real life. Okay, so this is like, I'll just write actually do the experiment. In real life. Okay, and what this basically means is we know that a tails can come up 1 out of 2 and a heads can come up 1 out of 2 because there are two options. There's a head and then there's tails. So there's two different options and each of them occur once on the flip of a coin. However, when you're actually doing experimental probability, you could roll or you could toss a coin twice and get tails twice. Or you can toss a coin twice and get heads twice. Okay, so experimental probability is the actual, like, physical experiment that you're doing. So even in these examples here, the probability of an event occurring is the number of successful trials. Number of successful trials, okay, divided by the total number of trials. Okay, for example, if you want the probability, we would write it probability of getting a heads. If you roll a heads 5 times out of 8, like out of 8 tosses, five of them come up heads, then the probability, the experimental probability of tossing a heads would be 5 out of 8. Now, the probability of an event is expressed as a value between 0 and 1. Okay, if something has a 0 probability of happening, then it's certain not to happen. If it has a probability of 1 to happen, it's certain to happen. Okay, the 0 means 0%, and the 1 actually means 100% it's going to happen. Okay, probability can be represented as a fraction or as a percentage. Okay, percentage, or as a decimal. Okay, so going back, let's just do a little reflection. Going back to this experimental probability, does experimental probability always give an accurate prediction? that an event will occur. Okay, so we are going to explore this a little bit more, and we're going to realize, give you a little pre-brief. The more time, the more trials, the more trials. And remember, a trial is one round of the experiment. Okay, the more trials that we do or that we conduct, the more it will tend to the actual probability, like the theoretical probability, and we're going to get into theoretical probability as well. The more the experimental probability, I'm going to write EP, will tend, we call it tend to, or like look like, to the theoretical probability. Okay, so let's do example 1, performing an experiment. Using a 6-sided dice, roll it 20 times and keep track of the outcomes. So what I did is I went ahead and like rolled a die 20 times, and this is what we got. So, or this is what I got. The number rolled 1. So like this would be the outcome. So when we rolled, how many times did I roll a 1? Well, I just tallied it, so 2. How many times did I roll a 2? 3 times. How many times did I roll a 3? 3 times. A 4, this would be 5, 6, 4, and 2. Okay, so let's go ahead and graph this. So I rolled a 1 2 times. So let's go zeros here. This would be 1. This would be 2, 3, 4. I don't like that. 0, 1. This will be the 2. 3, 4, 5, 6, 7, 8. Okay, so I rolled 1 2 times. Okay, I'm going to shade in 2 boxes. 3 times. 1, 2, 3 boxes. 3 boxes. 6, 4, and 2. So 1, 2, 3, 4, 5, 6, 4, and 2. There we go. Okay, so let's take a look at here. I'm going to actually tally these up and just make sure that they equal 20. 2 plus 3 is 5, 8, 14, 18, 19, 20. So this does equal 20. Okay, so a die was rolled 20 times. So how many times was a 5 rolled? Well, 5 was rolled 4 times. So 4 out of 20. And if you want to reduce this, remember, just divide the top number. You can do it simply, like just divide them by 2s. We notice that the 4 and the 20 are both even numbers. But then we notice the 2 and the 10 are even numbers, and you can divide both of these by 2 as well. Okay, so a 5 was rolled 1 out of 5 times. So find the experimental probability of rolling a 6, and then let's express our answers as a fraction in lowest terms, as a decimal, and as a percent. Okay, a 6 was rolled twice. 2 out of 20 rolls. Okay, which is actually 1 out of 10. Okay. If we take our calculators and we actually divide 1 divided by 10, we get 0.1. Okay, or 10%. So there's our fraction, there's our decimal. Our decimal here actually just comes from dividing 1 divided by 10, and then 10%. Okay, so the experimental probability of not rolling a 6, let's find that. So we know rolling a 6 is 1 out of 10. Okay, so we can actually think of it as the leftovers of 1 out of 10. So we can technically do like 100% minus that 10%, which is 1 out of 10, and we'll get 9 out of 10. However, we can also do it as like the sum of not a 6. So if we did the probability of rolling a 1, the probability of rolling a 2, probability of rolling a 3, which I get 2, 3, and 3. So 2 out of 20, 3 out of 20, 3 out of 20. The probability of rolling a 4, and the probability of rolling a 5, which are 6 and 4. 6 out of 20, 4 out of 20. So we can actually way, we can actually take every single probability here and just add it up. And why I didn't reduce any of these is because right now they all have the same denominators. So all we actually have to do is say like the probability of rolling not a 6. So we can say 6 prime, which means not 6, or we can just simply put not 6. Okay, we would just have to add the 2, the 3, the 3, the 6, and the 4. And again, the denominator is going to be the same because we didn't change it. So that's 10, 16, 17, 18. 18 out of 20, and when we divide each of the top and the bottom by 2, we get that 9 out of 10. Okay, so two different approaches. We can either take the leftovers of rolling a 6, and that would be not rolling a 6, or we can add up the probability of 1, 2, 3, 4, 5, and that would be not rolling a 6 as well. Okay, and let's take D. How would you expect the heights of the bars to relate to each other, and explain? So simply, the more times the event occurs, so I would say the more times the event or the outcome occurs, the taller the bar. The taller the bar. Okay, and the less times the event occurs, the shorter the bar. Okay, and that's of course on the bar graph. Okay, example number 2. The coin was tossed 30 times. The experimental probability of turning up heads was 2 over 5. So if we want to, the probability of heads equals 2 over 5. Okay, if we want just short form, explain what this probability means. So for every 5 times the coin was tossed, it showed up twice heads. It showed up heads twice. Okay, and how many times did the coin turn up heads? Okay, so that's actually out of 30. So we're gonna do, instead of reducing the 2 out of 5, because we can't actually reduce that, we're gonna multiply up to get an equivalent fraction over that 30. So what times 5 equals 30? Well, it's 6. So what's 2 times 6 as well? Okay, as long as we're multiplying or dividing both the numerator and the denominator by the same number, then we'll get an equivalent fraction. So an equivalent fraction to 2 over 5 is 12 over 30. So 12 of the rolls, or the tosses were heads. Okay, and then so what does that mean? How many times did it turn up tails? Okay, again, this is like the backwards. We're gonna take like the leftovers. So 30 out of 30 minus that 12 out of 30, we get 18. So it turned up tails 18 times. So 18 of the tosses were tails. Okay, what was the experimental probability of turning up tails? Again, this is it right here. Okay, 18 out of 30 would be tails, but let's actually reduce this. Let's divide them both by 2. Okay, 9 out of 15. 9 and 15 can actually both divide by 3. So let's keep going. That's 3 out of 5. Okay, so there's a 3 out of 5 experimental probability of turning up tails. And if you think about it, we have 3 out of 5, which is the tails, and the heads, which is 2 out of 5. If we add these, we get 5 out of 5. We get 100%. Which is perfect because 100% of those tosses will either be, they will come from tails or heads. Example 3. The following graph displays the frequencies in the number of females in families that have 6 children. Okay, so every single family has 6 children. So what this graph displays is the number of girls. Okay, let's answer the following questions. So let's just analyze the data in the graph. Okay, so how many trials were performed altogether? So how many families of 6 did this graph or this survey actually survey? So let's count these. So this represents 1 family. Okay, this represents 4 families, 6 families, and then these are 3 and 3. So let's just actually add these together. Okay, that's 10, 16, 17. Okay, so 17 families were surveyed, or they found 17 families that had 6 children. Okay, so the number of trials is 17. What is the experimental probability of having 2 females in a family of 6 children? So let's look up 2. That would be 4. So the experimental probability of having 2 females, and you can short form this, 2F, I'm going to understand what that means, is 4 out of 17. Okay, and according to this experiment, what is the average number of females in a family with 6 children, and how can you tell? Okay, what I would do is, we know that there are 17 families, so I would add all of these up. So this is 0 one time. There's no families with that they surveyed with 1 female, but we're going to count, there's 4 families with 2 females. So 1, 2, 3, 4. There are 6 families with 3 females. 1, 2, 3, 4, 5, 6. Okay, there are 3 families with 4 females. 1, 2, 3. There are 5 families with 3 females. Oh, 1, 2, 3, 4. Sorry. There are 5 families with 3 females. Sorry, there are 3 families with 5 females. 3 families with 4 females, 3 families with 5 females. That's right. 1, 2, 3. This is actually how to find like the actual average. Okay, so we can just go ahead and add those up, divided by 17, because there are 17 families. I would actually also probably just go with 3 as an approximate, so it should be around 3, and let's actually calculate. 1, 2, 3, 4. I get 53 divided by 17. Okay, 53 divided by 17, I get 3.12. So 3 families. I mean 3 females. So there's an average of 3 females per family. Okay, we can see that by the graph. We can also see that in the manual calculation.